All right, one thing I learned from first period is it took us all the way to the bell and we did not nearly get done as well as I wanted to. So we got to make sure we keep a good pace today. Our quiz is next class, so we want to make sure that you're getting everything you need between now and then. So right at 10:35, I'm going to start. If you have any questions about what we've been working on, I'm happy to field them now. And the only reason I wasn't here sooner is I just released first period like 1 minute ago. So if you guys have any specific questions, I'll hit on them now. But just know we're going to review almost everything that's been assigned over the last couple of days. All right, submit.
Can you do letter C on graph number 2 for the homework?
Graph number 2, yeah. Okay, so numbers, this is graphs 2, first page, letter C. It says determine the horizontal position of the cart. What you're going to, I'll talk you through this, but we're going to go through it as a class as well. But in order to know the horizontal position, we need to know its displacement, right? Because it tells us that it started at 2 meters, but we need to know the displacement. So what we're going to use is the area under the curve. So you're going to shade in anything between the curve and the x-axis. If you're above it, you're shading in above it. If you're below it, you shade in below it. What you should find is you have 2 triangles now. With those 2 triangles, if you use 1/2 base times the height, the area of a triangle formula, you'll have what's above the x-axis is positive, what's below it is negative. So you went forward, then you went backwards. Take those 2 values and add them together, plus your starting position, and that gets it for you. Now I'm going to do it a little bit slower in class only because it just hit 10:35. I'm going to show you your warm-up as soon as I can pull it up. Let me pull up the warm-up. And it's only going to be up for a second because, let me share Chrome. All right, this is your warm-up. Now, where you find it, if you go into our course, you can see that today it says James Corden position and velocity graph. Also down here, it says due today, submit finish James Corden position and velocity graph. All right, so you got to submit this. Now, what it is here. So I don't know if you can see it. Let me see if I can blow it up. There we go. There we go. All right, so if you remember James Corden from the Late Late Show, if you're still up at that time watching TV, he used to, I don't think he does it, let's see, who's in the waiting room? Admit them all. All right, now we had James Corden, so he's doing this carpool karaoke thing, and what you need to do is graph James's position over time and his velocity over time based on this story, okay? I don't want to leave it up because this is very valuable time. This is your individual assignment to do between now and midnight. I do have it worked. I can compare my answers to yours, but I want to get you ready for the quiz. This does help you get ready for the quiz, but this is your asynchronous activity. And like I said before, we went way over in first period. So let's bring us all back together. What I need you to get out, you turned in your storybook analysis. Get that out that you turned in. Also get your storybook position versus time and your velocity versus time. Those are the 2 things I did number 1 for, and then you guys answered the questions by doing 2, 3, and 4 and answering all those questions. I'm going to go through those. I'm going to keep I'm going to clip through at a pretty good pace, but at any time, if you need me to slow down and ask a question, you just got to get loud. I prefer talking over chat because the chat I don't always see until it's gotten old, okay? So let me switch over to this other computer. I'm going to share Chrome with you guys, and let's go into it. So this was the first one that I did. You already know number 1. I'm going to come up to the questions. It says, what is Albert's instantaneous velocity at 4 minutes? So if we just simply go to the velocity graph, instantaneous velocity just means the velocity at that moment in time. So if we go to 4 minutes and we move up on the graph, we can see it would be 100. Then it asks us, what is Albert's average velocity between 2 and 15 minutes? This is one that got asked a lot about. So what we need to do is we need to see where he is at 2 minutes. It looks like he's right around this 200-meter mark at 2 minutes, okay? At 15 minutes, we know he's at the 1,000-meter mark because that's the finish line. What we would want to do then is draw a line from one point to the other. Okay, you can do it mentally or you can do it physically, but forget about anything that's already graphed and you just graph it from where he is at 2 minutes to where he is at 15 minutes. So what we see is our change in Y would be 800 meters. Our change in X would be 13 minutes. So the slope of that line would be our velocity averaged across. So we would take the change in Y over the change in X. When I did that, I got 61.5. Now, this is based on the lines I drew, but it should be pretty accurate for you as well. Again, average across a certain length of time, you got to say, well, where was I at the first time point? Where was I at the last time point? Connect that line and then get the slope of that line. Okay, that was number one, the questions for graph one. Let me show you graph two because these are the ones that you did on your own. This is your position graph. I'm also going to scale up our velocity graph for number two. And this is all what it should look like. I did my calculations off to the side just like I did in class. So I knew it went 700 meters total, 13 minutes total. And then for those 3 line segments, I calculated the slopes so that way I could then graph them. Okay, going to the questions, what is Brangelina's instantaneous velocity at 2 minutes? Well, this is my velocity graph at 2 minutes. I come up, it looks like it's 50 meters per minute. If Brangelina had maintained this velocity the entire trip, how long would it have taken to travel the entire distance? Well, we know that distance or displacement equals velocity times time. Well, if we know that the entire displacement is 700 meters, and they give us, they're saying, well, what if we use the 50 the entire time? If we said displacement divided by velocity, that would give us time. It's a rearrangement of that equation. So 700 divided by 50 gave me 14 minutes. It's a rearrangement of the equation we know, displacement equals velocity times time. And so we just solve for time and we said displacement divided by velocity. All right, so now we're gonna go up to graphs 3, and I am intentionally moving a little bit fast because I'm not hearing questions and we've got so much more stuff to cover besides this. I just wanna make sure that what you had here was a little bit square, figuratively, not literally. So Xander, I graphed in green. Zach, I graphed in red. This is their position graphs. They started at the same point, same time. They ended at the same point, same time. What is Xander's average velocity for the entire trip? What is Zach's average velocity for the entire trip? So here we just basically said, well, how far did they go? 20 miles. How long did it take them? 23 minutes. That's true for both of them. They both took 23 minutes to go 20 miles. That means that how do these average velocities relate to one another? It's a tie. It's the same thing. They both moved at 0.87 miles per minute. Okay. That brings us to graph number 4, bringing this up and bring this up. And what do we have? What is Freddie's average velocity for the entire trip? Okay, so let's go back over to this graph. This one I want to talk about for just a minute more than the others because this one, it asks us 2 questions. What's their average velocity and what's their average speed? I want some classroom interaction. I want someone to tell me what is the difference between speed and velocity?
Velocity is like with displacement and then speed is with distance.
Absolutely. So what was his same person, Kennedy, what was his displacement during this time?
Well, I did the problem wrong originally, so I'm not sure, sorry.
Okay, no problem. Somebody help Kennedy out.
Was it 1,500 meters?
1,500 meters. That's as far as he went away from the origin, 1,500 meters. All right, so anybody tell me what was his total distance during this trip? Let's look at the segments. How far did he go in the first 5 seconds? Or 5 minutes?
750.
700 meters.
750, right? And then from 5 minutes to 7 minutes, how far did he go?
Another 750.
So what's his total distance right now?
1,500.
1,500.
Right. And then from 7 seconds to 15 seconds, how far did he go then?
1,500.
1,500. So what was his total distance then?
3,000.
3,000, right. So his distance was 3,000. His displacement from the origin was 1,500. So when we calculate velocity, we care about displacement. When we calculate speed, we care about distance. Like your car Your car cares about speed and distance with the speedometer and the odometer. But then when we overall look at the displacement, we're only looking at the velocity. So when we go back over to graph 4, question 1, it says, what is Freddie's average velocity for the entire trip? Well, his velocity was based on 1,500 meters displacement divided by 15 minutes, giving him 100 meters per minute velocity, average velocity. For his speed, he went 3,000 meters in distance divided by 15 minutes of time, meaning that his average speed was 200 meters per minute. Since speed doesn't care about direction, every direction he goes has a speed. Where with the average velocity, he had some positive, some negative, some positive, and that negative kind of took down his average. It's just like grades. If you get a really good grade on your first quiz and then a really bad grade on your second one, the average is going to be somewhere in the middle, right? So just like grades, velocity cares about direction, good and bad. Okay. I think there were some extra questions on this second page. So let me scroll this first page all the way at the top so it's ready for the next go around. Let's see that. Yes, there's some questions over here on the side. I think yours were still on the same page, mine printed on the next page. Let's see, it says, suppose you were only given this graph. What graph is that? All right, that's a velocity versus time graph. Show how to determine Freddie's average acceleration between 5 and 7 minutes. Here I wrote it out. It says acceleration is a change in velocity. There was a constant velocity from 5 to 7 minutes, therefore the acceleration was 0. Remember, acceleration is a change in velocity, just like velocity is a change in displacement. If I don't have a velocity, I'm not moving. If I don't have an acceleration, my velocity is constant. Okay. Then it says, show how to calculate Freddie's displacement. And I said, you just have to sum up velocity times time for each segment. So there's 3 segments here. There's a positive one, a negative one, and another positive one. So I just say V1 times T1 plus V2 plus T. Actually, I don't know why that said plus. That should be a times. Let's see if I can fix that. I did this right before first period, so it teaches me to don't do anything at the last minute. All right, this should be a times. There we go. So you're basically going to get the velocities for each segment times time, and then that add those up. So I had a positive one, a negative one, and a positive one. Because velocity times time is displacement. Okay.
I have a question on number 4, question 2, or graph 4, question 2.
Yes.
So what I did was get the average velocity on each of like the intervals and then kind of multiply that, but like the relation with the total. So like, for example, in the first interval, it's 1/5 of the total. So
yes,
like I did that with each one. Yeah. So I weighted it, but is there like an easier way to do that or like a faster way?
So what I did was I looked at the total distance traveled. If you can calculate total distance traveled and then just divide by total time. That way you're not having to worry about weighting it. Because yeah, if you do it that way, you absolutely have to weight it. And what if you can't accurately weight each one? You're going to introduce an error that's going to throw all your work off.
All right, thank you.
Absolutely. All right, if we're good on this, let's move over to, and let's put this aside and let's go to that graphs 1, 2, 3 and kinematics graphs. This is the thing that said that it was due next class on quiz day. And I just heavily requested that it's done for this class because I want to review it now. I want to make sure that we reinforce this information. We flush out a bunch of questions so you guys are confident going into the weekend and you feel competent when you come to class on Monday. So let's see if I can find which tab that's in. Yeah, here we go, graphs 1. All right, so let me open up my binder to that page. All right, graphs 1. Now, some of these I've filled in some answers where I felt like it was kind of easy and straightforward. Other places I'm going to ask you for them. This starts with a table, a data table, and it wanted us to graph it. So I put my points in and I put a best fit line. What you need to remember for a best fit line, you see how my best fit line spans the entire size of the graph. Your best fit line does not start with the first point and stop at the last point. If the graph exists to the left and to the right, your best fit line spans that entire area. You do not force it through the origin. Look at my best fit line. It does not hit the origin. My best fit line also does not intentionally hit any point. It's not a graph from first point to last point. It's just it tries to have the same trend and the same slope as the points and whatever, and it's meant to be kind of in the middle of the point, so it represents each point as best as possible. It is a straight line. It is not a connect the dots. Now I put circles on my line here at the bottom and towards the top, and those are the points that I used, or the positions that I used to do my slope. You don't have to do those circles. I do it so you can see where I got my information from. The further away you do your points, the better. Try to find those places it goes through the crossing points of the grid, or at least the midway point of a vertical or a midway point of a horizontal line, so it's easier to identify the value. So let's look at B, slope. We know that that's rise over run, change in Y over change in X. So I had 220 and 1290. Those are my two coordinates. I did my subtraction, got 70 over 10, do my division, I got 7. It says, what are the units of the slope? Well, it's meters over seconds, because my y-axis is meters, my x-axis is seconds, so it's meters per second. You get that straight from the graph.
Is it okay if we like have a different slope if we use like different points?
Yeah, as long as your slope is close to mine. If your slope is 27, I would say there's something seriously wrong. But if your slope is anywhere from 5.5 to like 8.5, somewhere in that range, the closer to 7, the better. I'm not saying mine's perfect, but yours should be kind of close. The only way you know the perfect slope is if you put these coordinates into a graphing calculator and it told you what the best fit line slope was. But what I got, I originally did this a year ago, and then I redid it today and I got 7. And that's gonna be the same true for your exams. If you have numbers that are similar, they're accepted. Your AP1 exam won't use numbers. All your values are gonna be variables. Maybe one question will use numbers. So we're not gonna dwell on your ability to do the math. We're gonna dwell on your ability to rearrange equations, select the right ones, and identify things in physics. So you're okay. Okay, what information about the runner does the slope of the line yield? So what does this tell us? What does the slope tell us about the runner here?
You can run 8 meters every second.
His velocity.
Right, it's velocity. The slope, the information that the slope tells us is the velocity. And in this case, we could say, what could we say about the slope here? Other than being 7 meters per second, what can we say about it?
Constant.
Constant, what else? One other word.
Positive?
Yes, those are the two I'm looking for. It's positive and it's constant. That's what we want to know. What is the significance of the y-intercept?
It's his starting position.
Yep, that's the position the runner was in at time point 0. So that is the significance. And what does it mean for the runner? Here I put that he had a head start. He or she was beyond, they were at a positive position at time point 0. So this is like your little cousin that you race down the street and you're like, you know, I can beat them. So, hey, why don't you start, you know, a couple houses up? All right, so let's scroll this up. What is the runner's position at 12 seconds? Well, in order to know that, I always start with my fact every single time. In this case, my fact is a formula. X equals V times T plus X naught. This is the formula we did on day 1, right? We have X equals V times T plus X naught. And I underline, that little line right there is just me underlining it because I need to find X naught. I need to find his starting position. I know the slope is 7, the velocity is 7, and I can plug in any coordinate for X and T. I chose one that I also used for the slope. So I plugged in at time point 2, my position was 20. That allowed me to solve for X naught. And I found with my line, my starting position was 6 meters. Now that I have X naught, I went back to the same formula and I said, okay, well, now I want to know what is X when my velocity is 7, my time is 12, and my starting position is 6. I put that together to get 90. Now, don't worry. I've been told by first period that this needs to be posted. I will get this posted. I'm going to try to do it by third period. But I want to make sure that the things that you've done, we kind of get those questions answered. So I won't dwell too long to copy it down because it's going to be available to you. What's more important than copying it down is that you listen, understand, and then you do it on your own without having it copied down. I guarantee you, you're going to learn it 3 times better if you do this on your own and then refer to my pages as a check, but just don't use my writing as the how-to. If you can get the how-to on your own, you're going to be so much further ahead.
Mr. Watley.
Yes.
So in which questions do we start with the fact? Do we always start with the fact on like position questions? Like we're asked what is his position at a certain time?
As often as I can, I start with a fact. Now, sometimes I get lazy because I'm in a rush. But a fact can be an equation. See, with DII, I have the equation written before I do anything. I always write the equations because it helps me learn them. I didn't memorize these equations. I learned them because I wrote them every single time I needed them. And that helps me learn what's going on and helps me identify things sooner. So my fact for these answers or these questions is simply x equals v times t plus x naught. That's my fact. And now I'm going to use it to solve. Now, sometimes a fact is more required, like the facts that I've been giving you, those written out facts, those are for your FRQs, okay? And sometimes you may not have a fact that you know of to use for it, but if you know one, it's going to help you.
So you recommend us to use facts as often as possible?
As often as possible and or practical.
Okay, thank you.
Absolutely. What is the runner's position after 16 seconds? So here we're just plugging in, we know the slope is 7, or the velocity is 7, the time is 16, the starting position is 6. We're plugging that into our formula. I got 118. Okay. This is just like, yeah, go for it.
Interrupt. So for your x naught value, did you just look at your like your line and then just kind of guess based on the starting position?
No, what I did is come back up here to DI, this first one. You see where I've got the formula written right here where my cursor is kind of moving back and forth?
Yeah.
What I did was I chose a position, a point on the line. And I said, well, when X was 20, time was 2.
Oh,
And
I see
then
now. Okay.
I knew the slope was 7. So I used that to solve for X naught.
Oh, okay. I didn't see that.
If our answers are off by 1 or 2 meters, that's fine, right?
1 or 2 meters on this one?
No, on D and II.
Oh, for like if you have 92 or you have 112? Yes, yes.
Oh, okay.
Because your slope is going to be a little bit off. Best fit lines, if I draw this line 5 times, I'm going to get 5 slopes. They should be able to be really kind of close together, but they're going to be a little bit different. So when you draw your line, I draw mine, they're going to be a little bit different, but overall we should be in the same neighborhood, right?
Okay. Thank you.
Mr. Watley.
What's up?
So for like D and 2, so like I took like my meters per minute and I just multiplied that by, you know, how many seconds
Yep.
it was going to take. And I got like the same answers as you. So could we do it that way or?
Well,
Yeah, me too. I didn't add X naught and I got the same answers.
you have to add X naught. What if the starting position was much bigger? All right, here X naught is small. What if X naught was 1,000? It wouldn't have worked for you. You have to add in X naught. Now here, you got lucky that it's a close or similar answer because your slope was a little bit different than mine and it forgave that little bit of X naught. But if X naught was a lot more significant, you'd have been in trouble. So I would say, don't forget the X naught. Don't
I
forget.
was just making sure it wasn't like it was just like a fluke. It wasn't like a thing.
It's a fluke. It's
Okay.
not a thing. Yeah. It worked this time, but I wouldn't bank on it. Let's go to second page. So second page is a little bit different. This one we're actually graphing the velocity based on the story. It says a man with a constant speed of 0.5 meters per second for 0.6 seconds. So if it's a constant velocity, it's flat, right? It's not changing. Constant velocity 0.5 for 0.6 seconds. Then it says it takes him 0.4 seconds to come to a stop. Well, if I'm at 0.6 seconds, that means he's going to come to a stop at the 1 second mark because it took him a full 0.4 seconds to get to that stop. A stop meaning velocity is 0. So the velocity goes down to 0 over that 0.4 seconds. It says that he stays resting for half a second. So that means he's down here chill at 0 because this is a velocity graph. 0 means 0 velocity, meaning not moving. Then it tells us that he speeds up to 1.5 meters per second, but it takes him half a second to do it. So then we go up to 1.5 meters per second at a half second, and we draw that fourth line based on the story. So the first thing says is find the slope. I numbered these line segments 1, 2, 3, 4. You can see that in the graph. And then the slopes 1 and 3 are easy because they're flat. There is no slope. There's no rise, no change in y. So the slope is 0. For number 2, I got negative 1.25. It is a negative slope. It's going down. I'm looking at the change in velocity over the change in time. Number 4, the slope I got is 3 meters per second. The second half of this question, it says, what does the slope represent? I'd ask it out loud, but you can already see it on the screen. You see that triangle? That means change. Change of velocity over time equals acceleration. The slope of a velocity graph tells you acceleration. The slope of a displacement graph tells you velocity. Slope of velocity graph tells you acceleration.
Why did you write meters per second squared?
Oh, because the slope is tells me acceleration. All right, so the slope is the change of x over the change in y, right? So it's meters per second divided by seconds. So if I was to simplify that, if I just wrote meters per second over seconds, it's kind of a crazy fraction. You can simplify that to meters per second square. Because remember, you're dividing the y-axis over the x-axis. The y-axis is meters per second. The x-axis is seconds. Okay, and then C, how far does the man travel in the first 0.6 seconds? Here it's asking us for the displacement, right? How far is he traveling in that amount of time? There we want to find the area under the graph, meaning that, wrong cursor. We want to take this 0.6 seconds right here, all the way to 0, and we want to get the area under the graph, which would be a rectangle. The area under the graph gives us displacement. We know that velocity times time is displacement, right? Velocity times time is displacement. And if we want to multiply the two things we're graphing, we look at the area under the graph. So C and D are asking the exact same question, but they ask it in different ways. C says, how far does he travel? And then DI says, find the area under the graph. It's the same thing. The area under the graph is the displacement. And he gave us the same time interval. So as soon as we do one, we do the other. For that particular one, let me find what page we're on, number 2. For C and D, I got 0.3 meters. So if you're doing this or if you've done this, that's the solution I got was 0.3 meters when I did it. It says, what are the units of this area? Well, it's meters per second times seconds. So the seconds cancel out, you're left with meters. Meters are the units that we use for displacement for this graph.
I have a question.
Go for it.
So if I were trying to find just distance, I wouldn't calculate the area under the graph, right?
Well, in this case, distance and displacement, we can use interchangeably because the person is always moving forward. They have a positive velocity. So distance and displacement are the same answer. So you still look at the area under the graph. If it's a velocity times time graph, you look at the area under the graph in order to get displacement or distance.
Okay. If it were like to go, like if the graph went into the negatives, then it wouldn't work for that, would it?
If it went into the negatives, for displacement, you would subtract the positive from the negative. For distance, you would ignore that it went negative and just call it positive.
Okay.
Any negative movement would be positive distance.
Okay. Got it. Thank you.
Absolutely. DII, what does the area under the graph represent? And I put again for a velocity versus time graph, displacement. So a lot of these questions are all kind of hammering into you that in a velocity versus time graph, the area under the graph is displacement. Let's see, what do we have? E, how far does the man travel in the first second? Now we're looking at the area under the graph all the way to the first second. Well, we've already calculated for the first 0.6 seconds. Now we need to calculate from 0.6 to 1 minute and add those together. From 0.6 to 1 minute, the area under the graph, the shape is a triangle. Before 0.6 seconds, the area under the graph is a rectangle. So just remember that 1/2 base times the height gets you the area of the triangle, which would be the area. Let's see if I can draw. This area, we have a triangle. I'm a terrible drawer with a mouse pad. So I've got, that's my triangle, and then here's my rectangle. So I'm basically I'm dividing this up into shapes that I can calculate. That first 0.6 seconds, I've got a rectangle. I know the base and the height. And from 0.6 seconds to 1 minute, I've got a triangle, and I can do 1/2 base times the height. Add those together, and I've got the entire area under the graph for the first 1 second. How far does the man travel overall? Well, we've got the first 1 second. We know from 1 to 1.5 seconds, he didn't travel at all. He was standing still. And then from 1.5 seconds to 2 seconds, we have a nice pretty triangle that we can calculate the area of, and we would sum all those together. Okay, so it's basically kind of doing the same exercise over and over. That brings us to the end of graphs 1. Is there any questions specifically about graphs 1 that I could answer before we switch to graphs 2, 3, kinematics graphs? Awesome. Let's move into the next one because time is of essence today. All right. And actually, I'm going to leave that shading in. All right, so graphs 2. They gave us the graph. You can see that I've scribbled in some shading there. So we've got this. It says indicate every time t for which the cart is at rest. This is a velocity versus time graph. So unmute yourselves. Tell me when the cart is at rest.
4 seconds and 18 seconds.
You got it. Answered it for the class at 4 seconds and 18 seconds. How do you know that? Tell me why.
Because when the velocity, that's when the velocity line or the line of the graph hits 0, which means that there's no displacement.
Right. And if you were doing this on an FRQ, you could say something like the vertical axis in a velocity versus time graph indicates the velocity. Anytime that the object hits the horizontal axis, that indicates 0 velocity, therefore, i.e. the cart is not in motion. You know, you can kind of turn it into sentences explaining that I'm looking at this graph and I can see the velocity according to the vertical axis. When it intersects the horizontal axis, the vertical axis is 0. It only intersects at 2 times, at time 0.4 seconds, time 0.18 seconds. Those are the only times this cart is at no motion because this is a velocity graph. If this was a position graph, we would read it completely differently. But with a velocity graph, it only hits 0 twice. Now it says indicate every time interval for which the speed, magnitude of velocity of the cart is increasing. So when are we increasing our velocity?
9 to 12 seconds and 17 to 20 seconds.
All right, any other volunteers?
I think that's that's right.
Everybody else just want to go with the crowd?
I think it's from, what is this? 4 to 9 seconds and 17 to 20 seconds.
All right, can I switch your 17 and say 18 to 20 seconds?
Oh, yeah, 18.
All right, there's your winner right there. Why? Tell us why.
Because, I don't know.
Oh, you're doing so good. Don't give up.
Well, okay. Because it's going back past the displacement.
Okay, you're right. Now let me give you different words. If you're going towards the horizontal axis, what velocity are you approaching?
0.
Okay, so you're coming to a stop, right? So if the graph is approaching the horizontal axis, it's coming to a stop. Whether it's positive to 0 or negative to 0, it's coming to a stop. So anytime it's approaching the horizontal axis in a velocity graph, it's slowing down. Has to be. If it's approaching 0, it has to be. If it's moving away from the horizontal axis, it's speeding up because it's getting further away from 0. Whether in the positive or negative direction, no one cares. It's still, I can run fast backwards, I can run fast forwards. So if we look at the graph, I got to use this other mouse. If we look at the graph starting at 4 seconds, we're moving at a larger and larger velocity from 4 seconds to 9 seconds. After 9 seconds, we start approaching the horizontal axis again. So that means we're slowing down all the way up to 18 seconds. At 18 seconds, we're stopped. After 18 seconds, we keep speeding up all the way to 20 seconds, at which time we maintain our velocity. So if you, in a velocity graph, if you're moving towards 0, the horizontal axis, you're slowing down. You're coming towards a stop. Anytime you're moving away from it, positive or negative, you're speeding up. Okay, so great answers. I'm glad we're engaged on this. This is really good. Yes.
Would it be 4 seconds to 9 seconds and 18 seconds to 20 seconds?
It's 4 to 9 and 18 to 20.
Okay. Yeah. Thank you.
Absolutely. Yeah, 4 to 9 and then, yeah, 18 to 20. I'm just making sure because I had a mistake on this earlier and I'll make sure that it didn't correspond to the screen. And then it says determine the horizontal position of the cart at 9 seconds if the cart has an initial position of 2. Okay, so if my initial position is 2, you can see my, see, I didn't write out the equation here. I just went straight to it because I was running out of time this morning. But what I did is I calculated the area under the curve for the displacement. So from 0 to 4 seconds, you can see my scribble on the graph. I had to get the area of that triangle. It's positive because it's above the horizontal axis. And I calculated that triangle to give me an area of 1.6 meters. And then from 4 to 9, my displacement was negative 2.5. That's the area from this 4 second to 9 second, this triangle. And it's below the axis, so it's negative. So now I know that I started with a 2 meter head start. I went forward 1.6, then I went backwards 2.5. I added all that up to say, well, my current position is 1.1. So this is just a simple, how much displacement did you have, positive and negative, where'd you start, sum it together, and that will tell you your position. The only way you can get your position using a velocity versus time graph is if you're supplied your initial position. If you don't know your initial position, you cannot get an absolute position on a velocity versus time graph. I'm going to scroll this up a little bit. D says, now we want to sketch the acceleration versus time. We've never graphed acceleration versus time, but do you remember how we went from position versus time to velocity versus time, and we just basically took the slopes? That's the same thing we're doing here. We go to our velocity versus time graph, we grab the slopes under the same time scale and graph it. So let me scroll it back and let's look. Come on, where's my cursor? Here we go. So we have a nice long negative slope for the first 9 seconds. So I'll go back to this other one. There's my negative slope, my negative value, constant negative value for the first 9 seconds. Then what happened? Well, now I have a positive slope up until 12 seconds. So go back down. This is the value of that positive slope up to 12 seconds. Then what happened? Well, it stopped. The slope is 0. The velocity was constant until 17 seconds. So my slope is constant for 17 seconds right here at 0. Because my slope was 0, so my acceleration is 0. Then I got a great big jump of velocity. My velocity increased from negative all the way to this positive. So it had this positive slope to 20 seconds where it became constant. So this was my slope, my positive slope up to 20 seconds. Then it became constant at 0, so my slope was 0, so my acceleration is 0. So I'm basically just taking the slopes of this graph and graphing the slopes. The slopes of a position graph give you velocity. The slopes of velocity give you acceleration. Same mechanism, exact same. That brings us to the end of graphs 2. So far, we're doing pretty good with time. I think I'm pushing you guys much better than I pushed first period. Are we okay with graphs 2? Awesome. If you're not, let me see, is there anything popping up in the chat? No, good, perfect. Yeah,
I just
keep
have a question.
go for it.
So for the first line on the acceleration graph, you put it like below the x-axis. Why did you do that?
Because the slope up here is -2. That's a negative slope, right? So that means when I graph it down here, I have to graph the actual value -2.
Okay, thank you.
Absolutely.
I have a question.
Go
So
for it.
on question C, you know how you put like x equals 2 plus 1.6 minus 2.5?
Yes.
Where did that equation come from?
So what I'm saying here is x is my position, and my position is basically my initial position, x naught, plus displacement plus displacement. So
Okay.
I don't know that this is a formula you're going to find on a formula chart, but it's basically saying, where did you start? Did you move forward? Did you move backward?
Oh,
Okay, add all those up.
oh, so it's just adding all them together. Okay,
Right, right.
that makes sense.
Anything else on graphs 2 before we retire it and go to graphs 3? Awesome.
Yeah.
Let's go.
Yeah, I have a question.
Go for it.
So, okay, so on the C, you use displacement plus the displacement of the same line. Or you got the area from the same line. So does it have to be from the same slope, or does it have to be? Or could it be
Well, they gave me the time interval, so 9 seconds. So I knew that I had to get everything from underneath the graph from time point 0 to time point 9 seconds. Well, from 0 to 4 seconds, it was all positive, and I could draw that as a triangle. And from 4 seconds to 9 seconds, it was all negative, and I could draw that as a triangle. And so my first triangle, I got the area and made it positive. My second triangle was negative, and based on the area of a triangle. So that's when you see where I did the math here is 0 to 4 seconds, my displacement's 1.6. That's based on 1/2 times 4 times 0.8. And then from 4 to 9 seconds, I got a displacement of -2.5, because that's based on 1/2 times, let's see, from 4 to 9 would be 5, and then from 0 to 1. So my math would have been 1 times 0.5 times 5. So I'm just doing the areas of those two triangles, recognizing one is positive, one is negative. And then they gave me an initial starting position.
All right.
Did that kind of answer what you were asking?
Yeah.
Okay. Anything else on graphs 2? And let me just erase that. And all right, this is the last in that packet, the big fat packet of homework. So let's look and see what we have. Kinematics graphs, they give us a data table. In this data table, we can see that we've got position versus time. And it says, in 2 or 3 sentences, describe the dog's motion. Before I start describing it, I like to graph it because I can actually see what's going on. So we're going to hold off on number 1 just for now so we can get the graph done first. Number 2 says, use a number line to illustrate the dog's motion. We can do that pretty easily. We can simply say, okay, well, at time point 1, what were we at? At time point, let's see, time 0, we were at 1 meter. So we're starting basically right here. And then we can see that we move over to 3 meters in the positive direction. And then all of a sudden he stops, and then he starts going backwards, goes past the origin, and then comes out there by the end of the time. So in a timeline, we don't usually use that very often, but I guess it's just another way to illustrate something. But if I used a number line to illustrate the dog's motion, that's what my number line would look like. There's not really time listed there. It's more just meters. It's just the displacement kind of going in order. I wouldn't dwell on number 2 more than what we've already done it, because I don't think you'll ever do that again. Number 3, this allows us to actually graph what's going on. Remember, for any graph, you put a title, you label your axis with units, and then you make sure the data is nice and spread out. So I've spread things out to where I've got all 4 seconds going across the bottom, and then I've got a span from +3 to -3 in my vertical axis. I plotted the points and drew the lines. It's nice and linear. I didn't have to do a best fit line because everything just lined up real nicely. From this graph, now we can go back and answer number 1, because looking at this graph, we can visually see exactly what this dog is doing. So where is this dog starting out? Somebody tell me a story about this dog. Anybody brave enough to tell a story?
Sure.
Go for it.
Okay, so the dog starts off 1 meter away from his food bowl.
All right.
He doesn't like it, so he walks away he walks to 3 meters away from the food bowl.
Okay.
And then he feels exceptionally hungry. So he walks back to the food bowl, but he sees a better food bowl 1 meter away from his original food bowl. So he passes his original food bowl and goes to the new one.
There you go. See, he started out ahead. He was at 1 meter beyond the origin, in front of it in the positive direction. He went 3 meters out, so he moved 2 meters forward. And then he pivoted and came right back, and he passed the origin and went 1 meter beyond it. What can we say about his velocities during this? Anybody?
It started off positive and then negative.
Okay, positive and negative. What else could you say about it?
They're both constant.
There you go. Those are the 2 words I'm looking for. It started positive, went negative, but they were both constant velocities. So is there any acceleration here? No.
No.
There's none. All right, so that kind of walks us through that. Let's see what else we have on this page. During which time interval is the dog moving forward? So what time intervals is the dog moving forward? Let me scroll back so we can see it. Just throw some answers out. When is he moving forward?
0 to 2 seconds.
0 to 2 seconds. When is he moving backwards?
2 to 4
2
seconds.
to 4. Yep. What is the dog's speed from 0.5 to 2 seconds?
1
So
meter.
from, what's that? Let's see. What is the dog's speed from 0.5 seconds to 2 seconds? So we want to know the slope of that line. And what did we get?
1 meter per second.
1 meter per second. That's what I got as well. We click over and make sure. Yes. And then what about on the downward trend from 2 to 3 seconds? What slope did we get?
2 meters per second.
-2, right, though? Okay, perfect. All right, that's what I got as well.
If it asks for speed, is it supposed to be a negative or positive?
Oh, you're right. You're right. I didn't even notice that. Yes, speed is always going to be positive. Y'all are both right, because she answered 2, and then I said -2, right? In my paper, I just went directly to seeing that it was negative, and I did not recognize that it was asking for speed instead of velocity. Speed is always positive, so very good catch. Very good catch. And actually, let me make a note in my sheet so that way I don't make that same mistake. What's dog speed from 2? So that's positive because it's speed. Sweet. All right, good job. Now where are we at? And then the dog speed from 3.5 to 4 seconds, it's the same thing because it's the same line segment. Find the dog's average velocity for every time interval and fill in the following table. So we've already filled it in. Now it's velocity, so now it is negative. So it starts at 1 and goes to -2. And then I graphed the dog's velocity. I hope you can see it. It's the red line that's in there. It starts at 1, and then at 2 seconds, it goes from +1 down to -2. It's the red line on top of the black. So it might not be the easiest thing to see, but also we want to make sure we're labeling the graph, labeling the axis, putting the units in, and then putting appropriate the appropriate intervals along the way. So that brings us to the end of this page. That's all of kinematics graphs. We still have 40 minutes of class. I needed 30 minutes for the last activity. So I have 10 minutes that we could use, 5 to 10 minutes, to answer any questions from graphs 1, 2, 3, kinematics graphs, or the analysis that we started with. We can move forward, that's fine as well. I just want to make sure that if I skipped over your question or if we were hurrying past anything, I've got all the tabs open so I can shuffle back and forth.
Can we do question 14 on graph 3?
Graph 3, question 14. All right, the initial position of the graph in question 13. All right, so we go to question 13. The graph above shows the acceleration of an object. Which graph correctly shows the possible graph of position versus time? Okay, so what type of acceleration do we have there? It's
Constant
positive,
positive.
negative, or 0.
Positive constant.
Oh, it's negative. So your T line, your x-axis here, that's your x-axis. The one with the arrow, this is the graph.
So it's negative.
Right. So we have a negative, and then so if we looked at number 13, which graph shows the acceleration of the object, which shows the position versus time. So if we have a negative acceleration, which one of these is a possible graph for that?
B.
Anything else?
A.
B.
I said D.
B.
D.
I think we got them all covered now. All right, let me pull up my sheet here. All right, so what I have, negative acceleration. All right, tell me why, can it be A? Let's talk about A first. Can it be A?
No,
Why?
because the velocity is constant.
Exactly right. If I were to graph velocity versus time, what I would see is that is a negative velocity that's constant. Oh man, come on. That's a negative velocity, which is constant. So I know their acceleration would be 0. Okay. Now, if I look at B, I've got a velocity that starts steep and then starts to go flat. You can imagine it kind of flattens out. So if I graphed velocity for this one, I would start, let's say this is velocity versus time. I would start something positive and then go to something towards 0. So like this, right? Is that about what the velocity shows me there? It starts positive and it goes towards 0, towards flat. Okay, let's do C real quick. I'm just going to draw all the velocity graphs for these position graphs. So this one, I can see that my velocity, my slope of this line is kind of 0, but then it gets really steep, really positive. So when I graph my velocity versus time here, I would start at 0 and then go positive. Okay, and then my last one, my velocity starts near 0 and then is really negative after that. So now if I do my velocity versus time graph, here I would start at 0 and then go negative. Okay, now that we've seen these, we've already talked about it can't be A. If we look at the velocity graphs alone, which one of these will work for a negative acceleration?
B.
All right, you said B? Anybody
Or
else?
D, maybe.
Oh, D? Okay. All right, let me see if I can, how many students I can show on the screen at once. All right, anybody vote for, all right, A is out. Anybody vote for B? Let me see your hands. Like 2 people say B. All right, what about C? All right, what about D? All right, everybody that voted is right. B and D work. B and D work. Both of those have negative slopes, don't they, in the velocity? Both of those velocity slopes, graphs that both of those velocity graphs that I wrote out, that I drew, have negative slopes, don't they? So that means they both have acceleration curves that are, or acceleration graphs that are negative. So B and D work for this. So 2 answers work.
I don't understand how you got the velocity graph for D again.
Okay, no problem. Let's look at this. So let me erase the things that I wrote so I can kind of rewrite them. Get rid of this, get rid of this, get rid of this. Okay, and then I'm gonna, as long as I didn't make a mistake, which is completely possible. So velocity versus time. Now, the slope of this line, of the graph that they drew for D, what would the slope be close to? If I drew like a parallel line, it's kind of near 0, isn't it? Isn't that kind of a 0 slope? Okay, and then down here towards the bottom, that's really a steep negative slope, isn't it? So if I do tangential lines and kind of do it along the way, you can usually the first and the last one give you an idea, but along the way, you can kind of figure it out. It starts here and then it goes there. So at time point 0, the slope was kind of near 0, right? So I'm going to put a dot right here. This is where it started. And then at the end of the graph, it was really negative. That means it was really negative, right? At the end of the time, it was negative.
Mhm.
So now I can draw it like that.
Okay. Okay. That makes
Where
more
if we
sense.
compare it to B, it started really positive. So if you look up at B, where I'm kind of making that dot bigger, it started positive, and then it finished out near 0, which is here.
Okay. I see it. Thank you.
So B and D work on that one. And I probably marked B on mine and didn't say B and D, because once I saw B was right, I just moved on. I was like, hey, there's the right answer. No reason to look at the wrong ones. And then 14 on this one says the initial position of the object in question 13. What about number 14 on this? I mean, I've told you the answer, but let's reason it out. The initial position of the object in question 13.
How can you tell the position from the acceleration graph?
Exactly right. D cannot be determined because we've selected 2 position graphs that could be right. So it's definitely D. We've got 2 position graphs that could be correct. I'll give you one other thing about this that you can shortcut. The position graphs that are shaped like a sad face. So if you were to put B and D together, and let me do this down here at the bottom. If I were to put B and D together, so D, let me erase that. So if I drew D first, so no, actually draw B first. So B looks like, yeah, B looks like this, right? We good on that so far? And then D looks like that. See how that looks like a sad face? Position graphs that have either side of the sad face, the left or the right or both, that is negative acceleration. If you have a position graph that starts out this way or this way, either side of a happy face, acceleration is positive. So if you ever look at a position graph and it's either side or both sides of a smile, positive acceleration. If it's either side or both sides of a frown, negative acceleration. Okay, we're going to get more into this after the quiz. We're going to have a whole, there's a foldable we build that you have for reference. And when you see that, you're going to remember all this stuff. But since you asked, I want to make sure I covered that. We're down to 30 minutes before class ends. If I know how to do math, which I can do sometimes, let's go into the last activity for today. So I'm going to retire that screen. And this is something that you can probably do in more detail as well when you're studying. I'm going to show you where the material is. So let me just make sure I have it accessible. Okay, here we go. This is our Canvas page. I know you guys have been here because you've had to submit work. And today is where we're at, Wednesday, right? And I showed you this James Corden position and velocity graph. And you can see that you submit it here. What we're going to do now is this scavenger hunt, position 1, number 1 position, number 2 velocity, and the last one graphs document. I'm going to go through the graphs document and then we're going to talk about it. But what I would advise is that you open up the answer sheets on your own, and this is what they look like. You get an answer sheet. This is the one for velocity, and it's like how many graphs show an object at rest. And some of them have one answer, some of them have multiple answers. There's an answer sheet for the position versus time, and you can go through that. But what we're going to do is we're going to go through each of the graphs and we're going to talk about them. And I would advise kind of going back and trying to match them up with all of these possible answers. It will help reinforce your ability to interpret the graphs. It's a skill that takes a minute to build, but once you have it, it makes things much, much easier for a lot of the work that we do throughout the year. So what I'm going to do is I'm just going to go directly to the PowerPoint, which is shared separately. So let me open the PowerPoint and now I can share it. And do it that way, do it this way. All right, so what we can do is we can go through the PowerPoint and then we can talk about what each graph means. So I'm not looking for specific words necessarily, but I'm going to kind of lead you to different things. So what do we have? All right, first graph. These are all going to be position versus time graphs. So I want everybody to unmute, kind of participate, throw words out there. I won't point and laugh. I'll either point or laugh. Okay, I won't do both. Just kidding. I'm not going to do that. At least I got 2 people to smile. That's awesome. 3 people are listening. What do we know about this position versus time graph? What can we say?
Oh, they're not moving?
They're not moving. That's true. What else can we say?
Velocity is at 0 and the acceleration is at 0 as well.
Okay. Where's the object located?
The origin.
Yes. Our object is at the origin. It has a constant velocity equal to 0. There is no acceleration. It's also 0. It's not moving. Those are all things we can say about this graph. What about this graph?
Velocity is constant negative.
Velocity is constant negative. Somebody else tell me about this object. What could we say? Could we make a small story about the object? Where's it starting at?
Origin.
The origin?
Which direction is it moving?
Away from the origin.
In a positive or negative direction? So these are things I want you to think about when you see these graphs. In a position graph, think about where is it in relative to the origin? Is it at the origin? Is it in front of or behind? Is it in a positive position or a negative? And then which direction is it moving? In its movement of direction, is it at a constant velocity, positive, negative, that kind of thing? So those are things that kind of come to mind as you go through this. What about this one? Now, everybody, anybody answer. I'm not restricting anybody. What do we know about this guy?
Not starting at the origin,
Okay. Is it moving towards the origin or away?
towards.
Okay, so it's starting in a negative position, so it must be moving in a positive direction towards the origin. What do we know about the velocity?
Is it slowing down?
It is slowing down. Is the velocity positive or negative?
Positive.
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 Why is it positive?
Because you're sloping upwards.
Okay, because the slope is, it's always a positive slope. And how do we know it's slowing down?
Because it's getting
closer to 0.
hard and closer to
Right,
The
the
slope
slope
is-
itself is getting closer to 0, right? Because the slope is more severe, it's steeper, and then it becomes more shallow, right? Okay. And when it hits the origin, that doesn't mean it stops, right? Only in a velocity graph would that mean. Here, hitting the x-axis just means it's hitting the origin, some arbitrary point. What about that one? What do we know about this guy?
the velocity is I don't know.
Is it positive or negative velocity?
Negative.
It's
Negative.
negative because it's a negative slope. For its position, how does its position change over time?
It moves
It goes
backwards.
Yeah, I can hear multiple people, so talk over each other. That's okay. I can still understand. So it goes from a positive position, it goes through the origin to a negative position. Is it speeding up or slowing down?
Slowing down.
slowing down.
Is slowing down positive acceleration or negative acceleration?
Negative. Oh wait.
Is it a smiley face or a frowny face?
Positive.
Positive.
It's a positive acceleration because it's that smiley face that we talked about, remember? So that's something easy to pick out on a position graph now that you know if it's a part of a smile, it's positive. What about this one? Positive acceleration or negative acceleration?
Negative.
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 Negative. Where does it start at?
The
The
origin.
origin.
Origin. Velocity, positive or negative?
Positive.
Negative.
Positive.
Positive.
Right. See how you wanted to slow down. You knew that the acceleration was negative, so you didn't want to say that the velocity was positive. This is like driving in your car and applying your brakes. You've got a negative acceleration, but you're still moving forward. So you still have a positive velocity. Okay. So remember, for the velocity, we're looking at the slope, but to know the acceleration, we know the tricks. And if it's a frown, upside down smile, it's negative. Okay. What about this one? What is our acceleration here?
Constant.
Zero.
There is
Zero.
none, right?
Right, it's zero because why is it zero?
Velocity.
Velocity is
velocity's
constant.
Exactly right. And is that velocity positive or negative?
Oh wait, no.
Positive.
Positive.
Right. So we have no acceleration because the velocity is constant. That constant velocity is a positive value. And what about the position? What is this? Showing us as in regards to position?
Starts
Where
at
are we
the
starting?
origin.
Where are we moving to?
We're starting at the origin and moving positively away from it.
Exactly right. We're starting in the middle of our house and we're moving towards the front yard. You know, we're going in a positive direction, forwards. Acceleration on, oh, let me switch out the order I'm asking. Velocity on this positive or negative?
Positive.
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 Okay, and then acceleration positive or negative?
Positive.
Positive.
Okay, and then our displacement starts at the,
Origin.
and moves
Away from it. Positive.
positive or
Away
negative?
from
Yes,
it.
positive direction. Yep, it's moving in a positive direction. What about this one? What's the acceleration here?
Zero.
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 When do we change directions in this?
Whenever it crosses the x-axis.
Oh, trick question.
We don't change at all.
We don't change direction because tell me about the velocity of this line.
It's constant.
It's constant. Is it positive or negative?
Positive.
Both.
No, this is a displacement line. So the velocity is based solely on the slope. So here the slope is a positive constant. So that means we're always moving forward at the same speed. In this case, if I were to tell a story about it, I would say that I'm in the backyard. I walk all the way through the backyard, through the house, into the front yard. So maybe the middle of the house is the origin. I just started behind my house and went through the house into the front yard. Constant forward movement. I just started behind the origin and finished ahead of the origin. Let's not confuse velocity graphs and time graphs. It's easy to confuse, and that's why there's like 100 of these slides. What about this one? What do we know about the position?
Begins at the origin and moves away from it negatively.
Exactly right. What about the velocity?
Negative.
Negative, is it changing?
No.
Does this
Yes.
line have one? Yes, it's changing because there's more than one slope here, right? So that means if the velocity is changing, is it a positive acceleration or negative acceleration?
Positive.
Why is it positive?
Because it's a happy face.
It's a happy face. Know your tricks. I mean, it's below the axis. So you're like, I don't want to say positive if it's below the axis, but you can be behind the origin and still have a positive acceleration. In this case, we said the velocity is negative, right? The velocity is negative, but the acceleration is positive. Do we have any real world examples of how can you have a negative velocity but a positive acceleration?
Maybe if you're like in your car and you put
Okay.
your car in reverse and then you step on the gas and you just like start slowly going backwards and then
Okay.
I don't
I was with you for so long because you had it so close. All right. So now if you're going backwards, perfect. You got a negative velocity. Okay. If I speed up going backwards, that's also a negative acceleration because I'm speeding up in the negative direction. But what if I'm going backwards, so I have a negative velocity, and I apply the brake? That is a positive acceleration because that's bringing me back towards going forwards, right? I've got to get back to zero to then go forwards. So if I'm driving backwards and I hit the brake, that is a positive acceleration because it's preventing me from getting worse. Let's say going backwards is getting worse. It's preventing me from speeding up in the wrong direction, and it's helping me to go forward. So that would be your real world example. It's not an easy concept. Yes.
How would you draw this graph on like a velocity time graph? Like how would it be drawn? Because it's a changing velocity.
Okay. All right. So let me see. I'm sharing from there. So let me stop sharing from here, and let me see if I can share over here. It's like challenge. All right. What am I sharing? Share application here. Share. All right. So what if I open up? I didn't want a new tab. All right, let me open something blank. And usually just have, oh yeah, here we go, grid. All right, and so I don't have the best memory in the world, but I want to say that that graph, right, so what was the question again, so I can make sure I draw the right thing?
Like how to draw a velocity time graph of the graph. It was like a position time graph.
All right, so what they gave us this, did it look like that?
And no, it was the other way. It was like, it started closer to the origin and then it like flattened out.
It went like that?
Yeah.
Okay. All right, so, see, I told you my memory is terrible. And then this is position versus time. And you're asking me how to make a velocity versus time from that?
Yes.
Okay, so what I do is I like the tangential line thing. So right here, I'm going to say, okay, it's starting out very negative and it's finishing very close to zero. So that means when I come over here, it's going to start very negative and it's going to finish very close to zero. So it looks like that.
Okay.
So the tangential line thing really helps, really, really helps. It seems kind of dumb a little bit, but if you just draw the arrows, the little tangential lines next to it, it will help you say, okay, at the beginning, is it positive, negative, or zero? At the end, is it positive, negative, or zero? Connect the two dots. So go back to this and share it, and let's do this. So share here. Okay, so when I go to acceleration, I'm just going to put it below it because it's based on that. So acceleration, and then this is time. This slope is a single slope, right? And it's a positive slope. So that means acceleration would look like this.
Oh, so it doesn't matter what side of the graph it's on.
Correct.
Like for the velocity. Okay.
Right, because it's a positive slope. I don't care if it's below the axis or above the axis, it is a positive slope. This slope is a single slope and it's going positive. So that means it's a positive acceleration. Don't worry, we're going to make a whole foldable grid that shows for every position what is the velocity and what's the acceleration. It'll be a whole little activity to do that you can put in your notebook that helps you see those easier. And let's see, all right, go back to this. And let me go back and share here, there. All right, so that's the one that we were just messing with. And we go there. What about here? What do we know about this?
No acceleration.
What about the acceleration? Oh, no acceleration, that's true. What about the velocity?
It's constant.
Positive.
Constant is positive. What do we know about the position?
Moving towards the origin.
Right, and what way did we start, positive or negative?
Negative.
Negative.
Negative, exactly right. All right, so we're about halfway done with time-wise, so let's just advance to the velocity graphs. So let me get us to those. All right, so you can see there's a bunch that I skipped. I don't know if you could see, but it goes all the way to U. We weren't nearly to U. So let's switch over to the velocity graphs and go through those and see how we're doing. All right, velocity versus time. What do we know about the acceleration here?
There's none.
None.
Okay, what do we know about the velocity?
0.
Constant.
Constant and 0.
Okay, what do we know about the position?
Stays wherever it was.
We're not moving. Do we know where we are?
No.
Right. What about this one? What do we know about the acceleration?
Constant negative.
0,
0. Why 0?
because the velocity is constant.
Exactly right. Oh, hold on a second. I'm mixing them up now in my head. I'm sorry. The velocity here, is the velocity constant?
Yes.
No.
No.
Oh, what did the velocity start as?
Origin.
Which is
Zero.
valued 0, right? So the velocity starts at 0. What does the velocity become?
Higher
Well, the velocity is more
or
and
more
more
negative.
right. So then if the velocity is going more and more negative, what slope do we have on this line? Is it positive or negative?
Negative.
Negative. So there's a negative acceleration, right? Because the slope of this line tells us the acceleration. Don't use your your position versus time trick now. Now for acceleration, you're going to look directly at the slope. Let's do a few more of these. What about this one? What is the acceleration here?
Positive.
It is positive.
Positive.
And what about our displacement?
You start off kind of, I mean, it like curves upwards, kind of like you start off.
Yep.
Not
You
moving
kind of
that
start
much
off
and-
kind of flat and then it would curve up, right? It'd be the right side of the smiley face. Let's do 2 or 3 more on these. I don't want you guys to lose too much wind because we're doing so well for a while. What do we have here? Tell me about when the line crosses the axis. What's happening there?
It's
Stop.
at rest.
Yep, stop moving. What happened before that? What was it doing?
You're slowing down.
Yep, so you were moving at a negative velocity and you were slowing down. What happened after it crossed the axis?
Put up
In which direction?
positive.
Yes. What about what's going on here?
Slowing down.
I am slowing down. What type of acceleration do I have?
Positive.
Positive. And what type of velocity did I have the entire time?
Negative.
Negative. The velocity is negative because it's below the x-axis. The slope is positive, so the acceleration is positive. All right, let's do 2 more. What type of acceleration do I have here?
Negative.
Negative.
What type of velocity do I have?
Negative.
Positive.
The velocity is positive because it's always above the x-axis. Is it increasing or decreasing?
Decreasing.
It's decreasing. It's going towards 0. This is where we're starting out fast and we're slowing down as we approach the origin because we're approaching that 0 meters per second or whatever scale we're using. All right, one more, last one. What's our velocity here?
There is none.
Constant.
Constant positive.
So just
Constant positive. There is something there. So we are moving. There's whatever value that is. It's a constant positive. What's our acceleration?
0.
None.
Exactly right. And then is our displacement constant?
Yeah.
No,
No. No.
It's not.
no, it's like linear.
Right. So since we have a velocity, we know that our displacement is changing. We know it's not constant. All right. So let me end this. I think I'm doing it from here. Okay. Now what you're going to find is there's some answer sheets. There's a ton more in there. I think it's advantageous to go through those